and over on our website you'll find a free little revision guide for you. All objects give off infrared radiation. Our main source of infrared radiation is the sun. Now we know this gives off radiation because we know it feels hot and we can see it. And infrared radiation is just waves of radiation or waves of heat coming down and hitting us. Now depending on what it hits, the type of surface it hits is going to affect what happens to it. So we can have a dark matte surface, or we can have a light shiny surface. Now if we have a dark matte surface, it is going to absorb much more radiation. It is also going to emit a lot of radiation as well. But it is very, very bad reflector. Light shiny surfaces, however, are good reflectors. But they are poor absorbers and they are poor emitters. Here we have arrangements of particles in a solid, a liquid and a gas. You can see in a solid they are very, very close together. They are in a fixed orientation, and you can see these tiny little dashes here are supposed to indicate how much they are moving, and this isn't moving very much at all. Here we have a liquid. Now, these aren't in a fixed position, but they're still very, very close to each other. Some of them are still even touching. And they're moving quite a bit, as you can see by these, but they're still quite close to each other. Gas has lots of space in between them. There's lots of movement going on. So if we think about the properties of this, gases and liquids can flow. And they can flow because they are not in a fixed position. Gases can be compressed. So if you think about a balloon, you can squash it, whereas you can't really squash a bottle of liquid because it will burst and then you're changing the volume. So a solid and a liquid have a fixed volume. Now, turning between these involves the transfer of energy. So if we're going from a solid to a liquid, we need to put energy in. And this is melting. From a liquid to a gas, again, we need to put energy in, and this is evaporating. Going the other way, we're generally going to get energy out. Going from a liquid to a solid is going to be freezing. And going from a gas to a liquid is going to be condensing. One last thing that is interesting, but you don't need to know, going from a solid to a gas straight away, skipping out the liquid, is called subliming. Conduction is a way of transferring heat in solids, and this is only going to happen in solids because it involves the particles getting heated up and wiggling around. And once they're wiggling around, they need to bump into the particle next to it. This will make the particle next to it wiggle around, and it will bump into the particle next to it. So by wiggling all the way along, we are going to be transferring the heat energy in the form of kinetic energy from one end to the other end. Now in a non-metal this happens quite slowly. If you think about cooking, if you're stirring with a wooden spoon, it's not going to heat up, the end of the spoon is not going to heat up straight away, but it will heat up eventually. And the reason because of this is because it's a non-metal and the particles move spaced quite far apart. If the particles were spaced close together, they wouldn't take very long to bump into each other. But if they're spaced far apart, they do take quite a lot of wiggling before they bump into the one next to it. Now, non-metals have something extra. They have free electrons. And what these free electrons do, and when they get heated up, they start whizzing around all over the place. So these electrons can go over here and they can excite this particle here and cause this one to move and start vibrating, even though the heat's here and this particle has only just started vibrating itself. So the electrons can do lots of whizzing around, exciting particles that are actually quite far away from the source of the heat, which means there are two different ways that they can get heated up or get excited, passing on their energy in a solid. Now this means it's going to happen a lot faster, so conduction in metals happens faster than it happens in non-metals because of the free electrons. Convection is the way that heat is transferred in a fluid. Now this fluid is going to be a liquid or a gas. When our fluid gets heated up, the particles start to move, and just as in conduction, they start bumping into each other. After they've been heated up and they move around, they bump into the one next to them and space forms, so they become less dense. When they become less dense, space is in between them and they start to rise. So they move up to the top. Now, when they're at the top, they're not being heated anymore. Because they're not being heated, they have less energy, they're doing less wiggling, they're not bumping into each other, so they start to become more dense. The particles get closer to each other, which means they start to fall. And as they start to fall, they go back to the beginning. And this is a convection current forming, because these particles here that have now become less dense will get heated up again, have become more dense, will get heated up again, become less dense and rise, they'll become more dense and fall, and become less dense and rise, and become more dense and fall. Now this happens in radiators, in your central heating. It's going to be what makes pans boil. It's also working on in the mantle of the earth, causing the tectonic plates to move. Condensation happens when water vapour in the air, so tiny invisible droplets of water, come into contact with something colder. And as they come into contact with that something colder, there's a transfer of energy. So the energy is going out of the water vapour and it's going into whatever it's touched that is colder, whether that's a glass, whether it's a mirror, or whether it's a window. And the water vapour, as it gets colder, it's losing energy, it will become a liquid. Evaporation is when particles turn from a liquid into a gas. Now this is quite a complicated topic because there are two things that need to happen. The particles need to be travelling in the right direction and they need to have enough energy. So here we have two particles which have relatively the same amount of energy as I've shown by the size of the arrows. This one is travelling in the right direction out of the liquid, so will evaporate, and this one is travelling in the wrong direction down into the liquid, so won't evaporate. Here we have one that is travelling in the right direction, so will get out of the liquid. But this one has much more energy, but doesn't travel in the right direction, so it won't escape from the liquid. So two things need to have enough energy and they need to escape from the liquid. Now here I've drawn something with a very, very large surface area. Things that have a large surface area are more likely to have liquid particles escape, so evaporation is going to happen faster. The examiners love asking about vacuum flasks because it brings together all the different ways that a heat can be transferred. Radiation, conduction, convection, and it talks about all the different ways that heat can be trapped, so evaporation, reflection. Now the easiest way to approach this question is just to take each part bit by bit, work out what type of energy transfer it is preventing, and then talk about it. So the lid here, this is at the top, we know that heat rises, so this is preventing energy loss by evaporation. The plastic case, we know plastic is a poor conductor, so this is preventing energy loss by conduction. The vacuum, there are no particles in here. Now if there are no particles, we cannot have convection or conduction because, well, both of those processes need particles to move. The shiny surface on the inside, that is going to be reflecting heat back in. Glass is a poor conductor, so it is not going to be letting any heat out of here. So take each piece by piece, work out how it is stopping energy transfer and write that down. And don't talk about energy transfer, don't talk about heat. Energy transfer is just a little bit more sophisticated. When we're talking about energy loss from houses, there are lots and lots of different things we can do. We can install cavity wall insulation. Now, in a brick-built house, there are like 2 layers of bricks with a gap in between. What they can do is just fill this up with like fluffy stuff. So it's like putting a duvet around the whole house. We can put loft insulation in. Again, this is just like putting a duvet on top of the roof of the house, because it's made of like a fluffy, like fiberglass wool or something like that. What it's going to do is to trap the air in there. It's going to prevent convection taking place, so it's going to keep in the house. Now, around the doors, we can put draft proofing. So those gaps around doors, we can put like, those big sausage dog things, and stop air getting out. Windows, we can put in double glazing. Round hot water tanks, if people still have them, these can be in the airing cupboard or in the loft. We can put a hot water tank jacket. So again, this is just like a big coat around the hot water tank. We can put thick curtains, and that will stop heat escaping. Now, when we're talking about installing any of these things, we need to take into account payback time. And payback time is the cost for it to be installed over the annual savings. For example, draft proofing is pretty cheap to install. It's only going to take like, I don't know, maximum 20 quid, but you could save that in a couple of months on your heating bill, whereas double glazing is going to take tens of thousands of pounds to install, and that may take years and years and years to get back the cost in your savings bills. Now, there are other things you need to take into account, like especially with double glazing, you need soundproofing, you need waterproofing. This is more likely to come up as like a big 6-mark question, but make sure you do your calculations for this, because these are going to be really important, and make sure your conversions between years, months and days are accurate. The other thing they might ask when talking about insulation is U values. This is just a value as to how good something is at insulating. The lower the U value, the better the insulator. There is a lot of maths in physics. There's no way we can get away from this. Physics could be described as maths with a lot of words in and a few graphs. So we need to be really, really good at our maths, and these are the rules that I get my students to follow when we are talking maths questions. First of all, get your magic physics pen. Now, my students laugh at me, but this is what I call it. So get a coloured pen, get a highlighter, get a different colour pen to the one you're writing in. Circle all of the numbers that you can see in the question. Use the units to work out what these numbers mean. Get your formula sheet, find an equation with all of these bits on, write down the formula. Now, this is generally, unless they give it to you, going to be your first mark. Write the numbers under the formula in the right place, do the maths, because that's generally only worth 1 mark, and then add the units. So even if you've forgotten your calculator, you can still get loads and loads of marks by doing all of these things. Now, units are so important. You have to learn these, but there's just no way we can get around this. For any of the maths bits that you need help with, pop over to my website and look at the books that I've got there. Loads and loads of stuff to help you with the maths and physics. You're also going to need to be confident in your standard form, your significant figures, and you're going to be confident in your rounding, because these are the sort of things that are really, really likely to come up in the exam as extra little bits, but might not be something you spent too much time on in your physics lessons. My website has loads of resources to help you with this. This is our equation for specific heat capacity. You should know that E stands for energy, M is mass, C is specific heat capacity, and theta over here is temperature change. Our units, energies in joules. Please make sure this is a capital J because a lowercase j is wrong and will not get you the marks. Mass is in kilograms. Specific heat capacity is in joules per kilogram degrees C, and temperature change is in degrees C. I have seen them ask as a whole separate mark, what is the units for specific heat capacity? I cannot emphasize enough how important it is learning your units. They are just absolutely vital. Other thing to be aware on this is there is temperature change, not initial temperature or final temperature. Look for the temperature change. They might ask you to work that out. The best thing to do for these type of questions is just practice, 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 practice. If you want to do loads of practice questions, you can pop over to a website and get my book, or you can go and look at my classroom channel where there are loads of questions for you. There are lots of different types of energy that you need to know. And a good way to do this is the acronym Geeks Lunch. Now, U doesn't stand for anything, it's just in there to make up a letter. G stands for gravitational potential energy. This is the potential energy that something has when it's about to form. So if you're holding a pen up in the air, it has potential energy, gravitational potential energy, because it is about to form. The first E is electrical. The second E is elastic potential. This is like stretching a hairband. Once you've stretched the hairband, it has a lot of potential energy in there because when you let it go, it'll get that energy back and you can spring it at somebody. K is kinetic. S is sound. L is light. N is nuclear. C is chemical, and H is heat or thermal energy. Now, you need to be good at working out what energy goes into something and what energy goes out of something. For example, if we have a light bulb, we know that electrical energy goes into the light bulb, but the energy that comes out is going to be predominantly light, that is our useful energy, and our wasted energy is going to be heat energy and sound energy. Heat energy is the majority of cases going to be the wasted energy. Pretty much everything produces heat as wasted energy. Anything that moves is going to have heat as wasted energy. But when I say it's wasted energy, it doesn't mean it is destroyed. It just goes away. It just dissipates. And it dissipates or dissipated into the surroundings. Now, what this means is that it spreads out so much that it's not actually useful energy anymore, because energy cannot be created or it cannot be destroyed. It just turns into something else, or in this case, it dissipates into the surroundings. When we're working out the efficiency of something, it doesn't really matter about the units, because we can be talking about useful energy or we can be talking about useful power. It doesn't matter about the units because you don't need to put units in the end. You can either leave it as a decimal or you can do it as a percentage. And if it's power or if it's energy, we treat it exactly the same way. So you need to work out what is useful and put that on the top, and what is the total and put that on the bottom. Now, sometimes you might have to do a little bit of maths beforehand. They might give you wasted and you'll need to work it out. But just remember, useful goes over the top of total. For loads more practice, you can check out my classroom channel or you can check out my book over on my website. Sankey diagrams are a visual representation of how efficient something is. The useful energy, the energy in, and the wasted energy. So here we're going to have energy in. Going over to the right is going to be useful. And then down is going to be wasted. Now these diagrams are to scale, so we can see here that the bigger arrow is going towards the right, so that means there's more wasted energy, more useful energy than there is wasted energy that is going down. The best way to do this is to work out the scale or just count the number of squares that you can see on the graph, and then remember we need to do useful over total to find the efficiency of something. Here we have one equation that is going to have two different sets of units with it. We're going to have electrical energy, and then we're just going to have normal energy. So for normal energy, we have energy, which is in joules, power, which is in watts, and time, which is in seconds. Now, if we're talking about electrical energy, our units change ever so slightly. For energy, they become kilowatt hours. For power, they become kilowatts. And for time, they become hours. Now, there's no trick or surefire way you can know which set of units to use. You just have to look at what they do in the exam question. And then you have to think sensibly, you have to think logically. Are they talking about energy? Are they talking about electrical energy? Are they talking, in kilowatts? Are they talking in watts? Are they talking in hours? Are they talking in seconds? And then you need to work out which set of units to use. This is particularly tricky, particularly mean in my opinion, section of the course, because they don't give you too much instruction on which set of units to use, but if you get it wrong, they will penalise you by not giving you the marks for the units. There is a definite trend in asking you questions about the cost of electricity. Now, to do this is fairly simple, but they don't give you this equation in the exam. The cost is just the number of kilowatt hours times the price per kilowatt hour. And to add an extra bit of complication in this, some of these might have a daily standard charge. So it might be 20p a day, and then on top of that, it's going to be 5p per kilowatt hour of electricity. This isn't too complicated to work out, but if you don't know the equation in advance, then you're going to get stuck because they do not tell you. If you want to do practice on this and all the other equations, you can go over to my Classroom channel, or you can pop over to my website and get my book, which has loads of practice equations for you. We can produce energy using lots of different things. There are some non-renewable energy sources, including coal, gas, oil, and nuclear. Nuclear is going to be uranium and plutonium, which is like a rock we dig out of the ground. Now, these are non-renewable because they are a finite resource. Once we've dug them up and used them, we cannot get them again. These take millions and millions of years to develop, to make themselves underground. Once we dug them up, once we use them, we can't get them again. Now, the top three are also fossil fuels, because once they are burnt, they release a large amount of carbon dioxide into the atmosphere, and this is contributing to global warming. And this isn't something we want to happen. Nuclear isn't a fossil fuel because it doesn't release carbon dioxide into the atmosphere, but it is non-renewable. There is a large range of renewable energy sources, and the best one for the situation will depend on a number of different things. Location, direction, what the local environment's like. So solar power is going to work best in a southerly located place, whether that's going to be on rooftops or whether that's a field. It's going to work better in sunny countries. Countries which don't get a lot of sun, it's not going to work very well. And the disadvantage of this is it's not very reliable. It doesn't work during the night. Wind is going to work very well on top of hills or out to sea, out on the coast. But the disadvantage of this, again, is it's very unreliable because it's not always windy. And some people don't like the look of wind farms. It also kills birds when they fly into them. Hydroelectric power involves building a big dam, pumping the water up to the top, storing it at the top in a big lake, and then releasing it as and when needed. So the advantage of this is that it's more reliable because the water's there ready and waiting for when it's needed. But the disadvantage is that you need to flood a large area of land for this to happen. Waves and tidal obviously need to be in a coastal location, and it's going to rely on the tide coming in and out and the waves going up and down. Again, this is going to be bad for any marine life that is living around there because they may be affected by the machinery that needs to be put in. Geothermal energy is going to work best in countries like Iceland or America, where they have large geothermal vents, that's volcanoes underground. Doesn't work very well in the UK, but they use the heat from that to turn the turbines. Biofuels can work well anywhere, but you need to grow a lot of things, then you need to burn a lot of things. And obviously the disadvantage of this are ethical disadvantages, because could you use whatever you're burning to feed people, because there are millions of people starving to death, and here we are burning fuel so that we can watch the football. To produce electricity, we need to have a turbine spinning, and this turbine spinning will go into a generator, and this will generate the electricity. Now there are lots of different ways we can get this turbine to spin, but the most common one is by the production of steam. Now for steam, we need to heat up water and turn the water into steam so it can spin the turbine rounds and rounds and rounds. Now there are loads of different ways that we can produce the heat to turn the water into steam. Now this can be by burning things, so burning our non-renewable fossil fuels, so like coal, oil and gas, in a nuclear reactor where the nuclear radiation will produce heat and that will turn the water into steam. Or we can set the turbine spinning by a hydroelectric power plant or by waves or wind turbines. We can turn the heat from geothermal or biofuels into heating up the water and turning it into steam. So all of the different energy sources have their advantages and disadvantages, but they all basically boil down to the same thing. We need to get this turbine here spinning. The national grid is the way that we get electricity from our power stations into our homes. So the power station generates electricity, and then a step-up transformer is going to increase the voltage so that when it goes through the pylons, through electricity cables, it is much more efficient so that we don't lose as much electricity on the way. It gets transmitted all over the place through the pylons and then down to a step-down transformer, so there is a voltage that is safe to enter our houses. Now in the UK that is actually 230 volts. After a step-down transformer, it can go into our house and we can use it in however we like. There are two different waves you need to know about. You need to know about transverse waves and longitudinal waves. Transverse waves are ones that go up and down like this, and longitudinal waves are like sound waves where things are spread out and squashed and spread out and squashed and spread out and squashed. Now you need to be able to label lots of different things on there. So if this is our midpoint of our transverse wave, you need to know the midpoint to the top or to the bottom is the amplitude. The top of one peak to the top of the other peak is the wavelength. Wavelength is measured in lambda. Now the frequency of a wave is the number of waves per second. So if this total thing here was 1 second, we would get maybe like 1.5, just under one wave in there per total second. Whereas if here to here was a second, you can see we are getting a lot less waves in. So the frequency is the number of waves per second. When we're labelling a longitudinal wave, what we have are areas of refraction and compression. Now this is going to be a sound wave, how a voice box will jiggle the sound particles, and then that will make its way to you. Now the big difference that you need to know for longitudinal and transverse waves is that in transverse waves the vibrations are perpendicular to the direction of travel. And I'm going to say oscillations because that's just the fancy word for it. And I'm going to say they're perpendicular to the direction of energy because that's what it is, the direction of energy of the waves. Whereas in a longitudinal wave, the oscillations are in the same direction, so they are parallel to the direction of the energy of the wave. It is really, really important that you use the word energy, not just movement of the wave or direction of the wave, but the direction of energy or the energy of the wave. When we're talking about the wave equation, we have speed, we have frequency, and then we have lambda over here, which is wavelength. Speed is measured in meters per second, frequency is measured in hertz, and wavelength is measured in meters. Now for frequency, it's really, really important that you have a capital H and lowercase z. Anything else will not get you the marks. When something is reflected off an even surface, like a mirror or a shiny plate or something, it's going to come down and it's going to bounce back off. When it's reflected off an uneven surface, because it's not going to hit directly smoothly, it's not going to bounce back off in the same direction. So that's why we don't get reflections off uneven surfaces. Now with our even surface, if we are going to draw a beautiful ray diagram, we need to put in our normal. We need to put in arrows to show the direction of the light. Now this is our incidence ray, and this is our reflected ray. So our light box will be over here. This is going to be I, and this is going to be R, where I equals the angle of incidence, and R equals the angle of reflection. Now, for reflection, I should always equal R. You're going to have it bouncing back and exactly the same angle to the normal. And remember, please always, always, always draw angles against the normal. When we have refraction, it's when light changes direction because it changes speed when it goes through a different medium. So that could be going from air into water, or from air into perspex block. It's going to change direction because it's going to change its speed as it's moving through it. Now, if we're going to draw ray diagrams again, we need to pop two normals in this time. There and there. We need to have our arrows on to show the direction of light. And then we need to measure all of our angles against the normal still. So this over here is going to be I. This is our angle of incidence. Tiny tucked in there is going to be R. That is R as well, and that is I. Now the pattern isn't quite as simple as when we're looking at reflection. Here you are going to have your angle of incidence being larger than your angle of reflection. They're not going to be equal. Now diffraction happens when we have a wave, which I'm going to draw here as a straight line, so it could be a longitudinal wave. When it passes through a gap that is smaller or a different size to the wavelength, what happens is that it starts to curve around like this. Now this is the reason that sound will travel around corners but light won't travel around corners, because sound will spread out. Now, you're going to get maximum diffraction when the gap is the same length as the wavelength. If the gap is much wider than the wavelength, it's not going to happen, or if it's a little bit wider than the wavelength, you're going to get a little bit of diffraction. You can see this happening in coves where water will come in, and then there'll be kind of like a narrowing as you're going into dock, or as you're going in where there are boats, and you'll get kind of like a curving pattern of the wave. Here is our electromagnetic spectrum, and you can see as we are going along we are decreasing the wavelength and we are increasing the frequency. So our wavelength is from here to here. Here we have a very long wavelength but very low frequency. Here we have a very short wavelength and a very high frequency. These ones over here are also going to have the most energy. Now you not only need to know the order, but you need to know what all the different things do. So radio waves and microwaves are used for communication. So obviously radio, but microwaves are used in your mobile phones. Microwaves are also used for cooking. Infrared waves are used for communications as well. So that's going to be the little button on the end of your TV remote control. That's infrared. If you look at it, it's a red button. Visible light is obviously used for seeing things, but an example you can give is a camera. Ultraviolet light is used for like security protecting things, so you can write on something in ultraviolet pen and it won't show up under visible light, but when the police check it, it will show up under UV lights. X-rays are used for checking people's bones, and then gamma rays can be used for cancer treatment. When we're looking at waves and sound, if we have a high-pitched sound is going to have a very, very close together frequency, whereas a low-pitched sound is where you're going to have a very, very low frequency. A low amplitude is going to be quiet, whereas a high amplitude is going to be a very, very loud sound. The Doppler effect is how a wave changes relative to the source or the person observing the wave. So as this car moves towards me, the frequency or the waves are going to kind of like be squashed together because it's moving towards me. And as it moves away from me, they're going to spread out. So it's going to sound differently, equal distance this side of me and this side of me. Here it's going to sound very high pitched, and here it's going to sound very low pitched. And this is all because as the waves are moving towards you, you're going to see a higher frequency and shorter wavelength, and waves moving away are going to seem longer wavelength and less frequency. Redshift happens when stars are moving away from us. Like in the Doppler effect, the wavelength gets stretched out, it goes ever so slightly into the red end of the spectrum, so the stars look red, redshifted. And depending on how red they look, we can tell how far away they are from us. Now the opposite of this is blue shift, where the wavelength is being squashed, so it's being shifted ever so slightly into the blue, and these are the stars that are moving towards us. There are two pieces of evidence we can see today for the Big Bang. This is redshift and cosmic microwave background radiation. So redshift tells us that stars are moving away from us. Now we can make an illogical assumption that if stars are moving away from us, at some point they used to be closer to us, or they used to be in the same place as us. So things that are moving away to us, we can work backwards and say they all used to be in the same place. And cosmic microwave background radiation is like the static you get on old-fashioned televisions or radios. And part of that is the leftover sound of the Big Bang. We can see it still going on, and it's coming from every single direction in the universe. So every single direction in the universe sounds the same. So both of these put together are evidence for the Big Bang. Well done for making it to the end, guys. That was a bit of a hard slog. If there's anything I can help you with, please let me know. If you want some extra extension materials, pop over to my website and get my book. Or you can go and check out the P2 and P3 versions of this video.